Hello everyone. In this video, me, Aishwarya, along with my teammates Roona.shree and Supriya are going to explain the price prediction machine learning model. To start with, we have a data set of house sales for the place King County between 2014 and 2015. Next slide, please. Let's start with the overview of what we would be covering in the later slides as we proceed. First, we start with the step overview of data, where we try to understand the data better and form a few hypotheses based on this understanding. Next, we have the EDA part, which is exploratory data analysis. Here, we'll be doing two kinds of analysis, univariate and bivariate. After that, we have the feature engineering step, where we will be trying new combinations of attributes which could best fit the data. Then, we have the model fitting process, where we will explore different models and figure out which model fits best for the predicted set of predictors, or in other words, features. And then lastly, we have compiled all our observations, which would then reveal which model fits best and predicts the most precisely among the rest of the models. So now, let's begin. Next slide, please. Okay. So this is the most important step, and we spend a good amount of time understanding the data set, and we have listed the purpose of each variable for further understanding. Next slide, please. We have assumed some hypotheses as per our understanding by reading the data set for the first time at the first glance. First one, does the grade have any impact on house price? Are houses with waterfront priced higher, or is it the opposite? Does older the house means lesser the cost? The house with high number of views costs less or costs more? Does the renovation have to do anything with the house price? And lastly, does the basement square feet have any impact on the price? We shall find the answers to these hypotheses while we proceed with the presentation. Next slide, please. So now let's start with EDA. First one being the univariate analysis. In the univariate analysis, one variable from the dataset is analyzed at a time. If we look at some of the graphs from the slide, starting from the top left price chart, we can see how in the price chart, majority of the prices are above the upper whisker. When we analyze the data, we found out that nearly 5% of the price data consists of outliers. Next, we have the chart where we analyzed how maximum number of houses in King County have 3 bedrooms. In the bathroom chart, we have found out that 2.65% of the houses have their bathrooms data fall in the outlier region. Next, in the square foot living chart, we can see how most of the houses are having square foot living area around the value of 2000, and the number of houses with square foot living area greater than this value keeps reducing. In the floor chart, we can observe maximum number of houses are with only one floor. And lastly, we have a graph with a view variable which shows that maximum percentage of the houses in the dataset have not been viewed. Next slide, please. So now we would like to mention some strange facts that we noticed by studying the dataset. Going with the first one. While analyzing the column ID, we notice that some of the house IDs are repeated, but with different sale dates. This means the houses are resold. There were total 40 duplicate IDs. Secondly, here we can see that the number of bedrooms is 33, but the square foot living and square foot lot area is very less than it should have been if we think logically. This implies that there could be some error in data entry. Next slide, please. Now, after analyzing the univariate attributes, we are here doing the exploratory data analysis on bivariate attributes. So to begin with, we have started with the attributes of our hypothesis that we initially assumed. Now, as we start from the top left chart, here when we compare the mean price versus the grade of the house, we can see higher the grade of the house, higher is the price. So from this, we can say that we can move forward with our first hypothesis for deep diving. In the second figure, here when we compare the average price with the number of views, we observe that the house with less number of views has lower cost and are being sold in less time. Here as well, we can take this attribute for deep diving and checking for causation. Third, in the next figure, we are trying to compare the age of the house, that is, how old the house is, with the price. And here, as you can see, we can't find any strong inference to interpret anything. Now, if you go to the bottom right chart, we are comparing square feet basement with price, and we found out that again, we can't find any interpretation to our hypothesis. In the chart to the left, we are trying to compare the waterfront with price, and we observe that people are trying to pay more for nature beauty. And in the last one, we compare the year renovated with the price. And we notice that as the house is renovated, higher is charged to be sold at higher price. Next, I would like to call upon my teammate Supriya to explain the further slides.
Thank you, Aishwarya. Next slide, please. Yeah. After the bivariate analysis for all the attributes relating to our hypothesis in the previous slides, here we have found the collinearity among the variables like square foot living, square foot lot, square above, and the basement. And to do so, here we have used the scatter matrix to graphically represent the correlation. Next slide, please. Yeah, here we have represented the correlation between the attributes of our dataset in the numerical format. By this, we can find the degree of collinearity among the attributes variables. And in the right table, we have tried to show the correlation of other attributes that can be said as a predictor versus the price, which is our target attribute. And we can clearly see that square foot living has a highest correlation with price, that is being 0.70, followed by grade, that is 0.66, and then followed by the square foot living. And here we can see clearly that zip code has the lowest correlation with the price. So as we see square foot living, square foot above, and the square foot basement showing high correlation among themselves. So we have one thing to note over here, that we must not fit all of them together in the building linear model, as these attributes will compete among themselves and will lead to multicollinearity. So obviously we don't want two different variables representing the same influence on our target prediction, right? So next slide, please. Yeah, coming to this, while fitting the model, we saw that in previous slides, most of our attributes were linearly correlated among themselves. So here we choose the linear model for our analysis. Here we do the multivariate analysis to select the feature. And since it won't be feasible at all to combine all the attributes to find the best feature, as it may end up with huge number of combinations. So here we are using the greedy algorithm technique, which is also called as backward elimination or forward selection technique. So coming to the backward elimination, here we evaluate the model by taking all the attributes together to predict the price. And then we remove the features that do not significantly affect on the target value prediction. And then here as well, we can see by taking all the attributes together, our model didn't perform that well. So we would eliminate few attributes for the performance increment. Next slide, please. Yeah, coming to the forward selection technique, here we do the reverse. Here we add the first variable with the highest collinearity, that is the square foot living that we saw in the previous slides, to be 0.70. And over here we take the square foot living along with the other attribute one after the another, and we see that which gives improvement to our model. And in this slide as well, we could see in the same way we have shown our model performance increment from 26.41% to 63.75%. So next slide, please. Yeah, feature engineering. Here we use this technique to train our model by adding a new feature from an existing feature. And here we have added the feature zip code dummy by one-hot encoding the existing zip code attribute in our dataset. Why we have done so? We have done this because if we take only the zip code attribute, it is a nominal attribute in our dataset and it can't be fitted to a linear model. So we have encoded it to convert it into a categorical data to fit onto our model and then to check its performance. Now coming to the next feature, here we have added a new feature of age, which we have calculated by the year built and the year it was sold. This we did so as to check whether this feature has any impact on our target value, that is price, or not. Next slide, please. Yeah. Coming to the next feature, basement present. Here we are checking whether the house has a basement or not. And we have used the existing feature, that is basement present, square feet basement in our data set. And here 1 means the house has a basement and 0 means it doesn't. And coming to the fourth feature, that is renovated. This is also a categorical attribute, and here it says whether a house is renovated or not. And now all these 4 features we will be fitting onto our model, and then we can check for the performance. And now I would like to call my teammate Roona.shree to take on the further explanation. Thank you.
After torturing the data, now we are ready for fitting it into a linear regression model. And we have some 4 feature set. We started with the first one, which looked very obvious, the square feet living, bedrooms, and the bathrooms. But what we see is our score is, or the model performance is not good. So what we learned is, as Supriya told in the previous slide, if the features among the feature set are correlated among themselves, then this will destabilize the linear regression model, and we should avoid doing it. Our next feature set was square feet living with the other features like grade and waterfront, which increased the performance to a little bit. The next one again, square feet living, grade, and few other features, and which again increased our score to 0.64, the R square score to 0.64, which was quite motivating, but still not good enough. Then we did include the zip code, the encoded one, which we did in features transformation and engineering. We included that. We included few more parameters like basement present or renovated. And then we added one more feature, which is square of the square feet living. That boosts up our score to 0.82, and we are now all set. With that, we tried some feature transformation as well, like taking the log of a square feet living, which in fact reduced our R square score, which is quite obvious because it is reducing the impact of the highest correlated feature. We did the square of a square feet living, which increased our R square score, and we added that in our final feature set. We played around with squaring all the other predictors, but it increased the R square score. But when we did the final testing, it in fact gave us the bad accuracy for the model. We did try the square root as well, but again, it reduced the R square score. Now we have the final best feature set. We fit the decision tree with that as well. And what we found is the performance score of decision tree algorithm is not as good as linear regression. Also, what we have observed, as we are increasing the max depth, the performance was increasing. But after a certain limit, which is 8, the increase in the model performance was very negligible or minimal. So we decided to stay with the max depth as 8. Now, this is the last one, in the last phase, where we put our test data into the model which we have created, and the feature set which was giving us the best result while validation. And this gave us a very good score on the test data as well, which is 0.8188. And we are quite happy now. So all our codes are in the link, which is there in the slide. So thanks for hearing us out. And now please enjoy this video, which shows like we had real fun while doing this assignment.